Welcome everyone, and thank you for attending today's Parasoft presentation on object code structural coverage for DO-178 C. My name is Ricardo Camacho and I'm a Senior Technical Marketing Manager for Parasoft. I'm also accompanied by Uwe Kronholm, one of our senior software engineers, who will be presenting on object code verification. On the agenda, I'm going to start with a very quick informative glance at the challenges DO-178 C poses and how Parasoft helps you with those challenges. I'll then pass it over to Uwe, where he will be going in depth about how to achieve object code verification. Then we will finish it up with Q&A. All right, let's get started. Here I've laid out some of the key challenges in the standard for you. Take note that some of these challenges are triggered based on your software level or design assurance level, DAL. You will definitely need to perform bidirectional requirements traceability. Make sure you have a solid requirements management solution in place. Make sure you know which compliance objectives you need to satisfy. Document and mark them off as you go. Also, validate on your target hardware. Remember, it's a system that's getting certified. Adopt the coding standard and make sure you comply to it. There is MISRA, AUTOSAR, CERT, or define your own custom or hybrid of these. Make sure you perform and document your data control coupling analysis on your code if your DAL requires it. Perform structural code coverage to ensure that you've tested all your requirements. And perform assembly code coverage if your DAL requires it. Use a tool that has a TÜV certification history, but most important, make sure that there is a tool qualification kit available for use on the development ecosystem that you have. Finally, have a compliance management plan, an expert DER that can help you through the certification process. So let's go quickly through some solutions available from Parasoft in helping you with your challenges and goals in achieving compliance and certification. Requirements traceability is crucial in DO-178. Parasoft has built bidirectional integrations with some of the leading ALM tools like JAMA, Polarian, and Codebeamer. These integrations help fulfill the traceability from requirements to test cases, then down to the code and code review if desired. It also helps fulfill the traceability matrix, which is used for verification of requirements and the tests that validate them. The middle image shows a snapshot of our compliance reporting and analytics dashboard. Parasoft DTP is a fantastic reporting solution. Parasoft is a leader in coding standards compliance. We support the complete Cert C and C++ rule set, and this is the same for MISRA C 2012. We are leading in the industry on AUTOSAR C++ 14. We are a provider to primary contractor on the JSF coding standards. We have also been certified by MITRE as CWE compatible, and you see that I have also included DISA, the Defense Information Systems Agency. DISA provides a variety of security technical implementation guidelines referred to as STIG that give guidance for securely implementing and deploying applications on Department of Defense networks. Newly added is FACE, the Future Airborne Capability Environment, which defines some coding rules in the standards which we support. On-target hardware verification is one of those key objectives in DO-178, and Parasoft supports a vast number of embedded ecosystems. Our list continues to grow as our customers' base expands. We refer to this as cross-platform testing, which allows Parasoft C++ test cases to be generated and extended from the host environment onto environments that the software will execute, which might be a target embedded device, a simulator or emulator, or another platform to which you have ported your software. With Parasoft, you can automate unit testing to verify low-level software requirements, as well as high-level requirements with integration testing and system requirements with system testing. Your testing is simplified by way of a graphical UI so that users can specify their inputs and outputs and expected results. Test cases are nicely organized, making maintenance or edits to your test cases very easy, and execution can take place on your host and or target hardware. In addition, Parasoft tools can automatically generate test cases for you, expediting your unit testing and code coverage tasks, shortening the testing lifecycle, giving you huge cost savings. Regression testing will also be a breeze with the testing infrastructure in place and change-based testing. Just rerun your test cases on the new code. Huge savings in labor, effort, and time. Another great benefit from Parasoft is our code coverage capabilities. Enable code coverage, and as you execute your test cases, the coverage of every statement, branch, and modified condition decision coverage can be obtained, or any combination of these. And if you apply structural code coverage during system testing and you execute all your system test cases, the coverage results will tell you how much of your code was executed. Remember that for DO-178, you are using code coverage to ensure that you have not missed testing of any of your requirements. One amazing feature we provide is called Coverage Advisor. It informs you of the inputs and their values that are needed in order to obtain coverage for those really hard to reach lines of code. Again, our automated test case generation capabilities also contribute to obtaining structural code coverage, and these test cases are smart test cases. They look for use of null pointers, test your boundary values, look for division by zero, and much more. Uwe will go over object code verification, which is another step of code coverage granularity. As you know, tool qualification is a mandated process for safety-critical software development in DO-178. Parasoft's qualification kits for Parasoft C, C++ tests automates the process of creating the supporting documentation required for tool qualification of static analysis, unit testing, and code coverage, reducing both the potential for human error and time taken to perform tool qualification. I also wanted to add that Parasoft C, C++ test is used in safety-critical applications and has been qualified for use in other industry standards. Parasoft also provides a development testing platform where the testing results are analyzed and continuously tracked, which provides progress towards achieving compliance. So with Parasoft DTP, management and the team will be able to view real-time comprehensive results on static analysis, code quality metrics, unit testing, code coverage, progress on your testing to requirements, and more. Parasoft's DTP flexible drag-and-drop dashboard provides over 50 out-of-the-box widgets, categorized and color-coded so you can quickly assemble your own view into your quality process. Centralized aggregation of verification and validation results makes compliance easier by automatically generating the reports needed to demonstrate compliance. To further put Parasoft in perspective, we offer software verification solutions that address many of the verification objectives defined in DO-178C, as you can see from this infographic. Starting on the left-hand side, we have integrations with ALM tools or requirement management tools, providing the traceability to test cases and down to code. On the right-hand side of the V, we provide various testing tools and methods at the different levels of abstraction in the software development lifecycle. Testing methods like memory debugging, fuzz testing, API testing, UI testing, service virtualization, of course including static analysis, unit testing, and structural code coverage, and so on. That was a quick glance at some of the challenges in DO-178 and hopefully very informative on how Parasoft helps you address these challenges. Let's jump into object code structural coverage. Introduce yourself, Uwe. Over to you.
Hello, my name is Uwe Kronholm. I am a senior software engineer at Parasoft. Today I'll be talking about object code structural coverage for DO-178. Specifically focus on methods to reduce testing effort and achieving goals as quickly as possible. First off, I'd like to start with some focus, criteria, and methodology just to set a baseline for expectations throughout the presentation. Criteria for the high-level source code is that it has qualified for safety critical under DO-178. It has achieved acceptable standards for requirements-based testing, as well acceptable standards for MCDC, modified condition and decision coverage, and most importantly, is required to meet the criteria for level A acceptance, that of which being structural object code coverage. For this presentation, I'd like to focus on establishing correctness at the object code level in such a way that we reduce the scope of effort needing to be done within object code. Establishing the correctness for a whole translation unit is quite a formidable task. So we want to focus on small, what I call gap sections of deficient structural coverage that we can achieve in isolation. Methodology to that end will be applying object code instrumentation to the results of all of our testing practices that we previously instrumented at the source level in order to achieve those previous source level goals. We'll be instrumenting, starting at a baseline of getting coverage for our requirements, MCDC, and on-target or production testing gets the process of attaining 100% object level structural coverage very close to a final result without ever looking at the object coverage. And then what we can do with those results is produce cumulative reports so that we have a combination of our testing infrastructure for all methods of testing with instrumentation at the object level in order to show our cumulative coverage. All right, now I'd like to start with a very simple example showing the differences between MCDC measurability from source level and assembly level. We can start here with a very simple logical expression packed into a function. This is an if-else-if construction. And for generating a truth table for MCDC coverage, this is a simple A or B expression. To solve an A or B expression, we need to hold our A and B in isolation to prove validity of each parameter. So what we wind up with is a 3-run analysis that produces 100% MCDC coverage for this function. You can see here that we have A and B held in isolation, as well as example parameters that test that isolation. So let's move to the equivalent assembly construction under default compilation parameters. When we run each parameter set, we produce sections of coverage for the equivalent assembly. Run 1 covering these sections, jumping between 20 and 30. Run 2 covering these sections and again jumping between lines 16 and 21. And then run 3 with parameter 5, jumping between these sections. So let's consider we are testing in isolation for MCDC at the assembly level. And we start from scratch. We have no coverage from our source level, so we're just attempting to gain complete coverage for this piece of assembly in isolation. We would run our runs 1 and 2, and this looks consistent and complete with omitting our 3rd run. However, if we omit our 3rd run, we have achieved complete coverage. We have missed 1 branch statement coverage, which is a common occurrence. If we start from the perspective of the MCDC from source level coverage, we would have already had this 3rd run in and had complete coverage at the assembly level without doing any testing specifically for producing extra coverage at the assembly level. So let's move in now to an example that is more relevant or is a common occurrence in unit testing, and this is the deficient structural object code coverage for conditional branching. A translation unit, a high-level language, requires a compiler to produce assembly off of it, and the compiler is going to do things that are necessary and kind of implicit to the upper level language in order to keep the unit that it's translating in check. So these types of structures are boundary checks, logic inversions, and branch optimizations. In complex situations, the testing at the high-level source code level is going to be insufficient because the compiler will be injecting special checks or special logic around the constructions used during translation. We can adopt strategies to limit our need for assessing the assembly if we work specifically from the unit test that we produced high-level or source-level coverage for. And this is a note from the practical tutorial on modified condition decision coverage about MCDC achievements at source code level do not guarantee MCDC coverage at object level and vice versa. So I'm going to show first my testing interface and parameterized sets for high-level source. So here is my source code marked up with MCDC coverage in my quest to achieve 100% coverage at the source level for this C code. Here's an overview of the functions within my translation unit. You can see here the one we're going to focus on is a portion of this isRec knowable, which has achieved 118 out of 118 covered conditions tested in mostly independence. And then here is my panel showing the parameterized unit test cases specifically for the sections of isRec knowable, lines 70 through 195 that you can see on this side. So this is what we'll be focusing on here. So this has unit testing for MCDC at the source level with instrumentation in order to provide recording of source level modified condition decision coverage. If we take the same unit test with the same parameterizations instrumented at the assembly level, we can produce this report here. This report shows the interleaving for the lines 170 through 181 of the original high-level source code for isRec knowable, as well as the x86-64 assemblies with indexes from 599 to 634. If we look at the cumulative results for this, the run of the MCDC test with parameterizations, we can see that our branch coverage is 97%, 326 out of 336 for the function isRec knowable. Within this screenshot, we do have a single deficiency that we'll be covering now. This is the starting point for our testing of structural object coverage. And this deficiency at index 630 is a lack of a jump if above to L51. So we want to exercise this extra true side of a jump statement, or that extra path. The key is here for reading these indexes for coverage. I'm not going to go too deep into figuring out or debugging the assembly itself in this case, but what happens is this is an enum in a switch statement and we lack an outside of the boundaries of the enum value that's being tested. The compiler produces a check for a boundary check for this out of enum space. So what we can do is, in this case, I like to copy my parameterized test, the one that I showed you before. I duplicated and produced one single parameter for this to put my enum value outside of the range so that we can check this path. In testing this in isolation from my other unit tests, it allows me to see that my coverage path for this single parameter does exercise the section that I want to add coverage for or amend the gap that's missing here. So you can see in this report, I'm reporting on the instrumentation for my single parameter in the new unit test. So in this case, we have partial coverage culminating in actually taking this jump if above to L51 on index 630. So that green pip there is what we're looking for as an additional amendment to our original MCDC structural coverage. So now you can see I've merged the results from both the source level MCDC parameterized unit test with the single parameterized test for the gap that we are missing. And we now have positive coverage for the section that we are interested in from the original MCDC. As well as you can see, our coverage has moved up from 326 to 332 out of 336 for the function isRec knowable. Do note in this case, I went back and fixed all instances of this type of error or this type of deficiency so that we could carry this test forward into the next example. Now for the next example, I want to show something slightly different, something that can't be exercised through unit testing. It could be argued that the previous examples direct traceability is in question. It could be said that, yes, of course, there's going to be an implicit check for the out of bounds on an enum because you can't trust whether it's going to be an enum or another integer type. In this case, we are looking at constructions made by a compiler during translation that are of the class of no direct representation. Examples of this class would be file formatting, functional interfacing, and machine or operating system checks. The strategy for collecting this coverage data is the same as the previous one. However, the item we are instrumenting instead of a unit test, in this case, will be a production value, production executable. The executable is instrumented and then run in a standard environment and exercised in order to send it down a path appropriate for exercising the deficient piece of structural assembly that we need coverage for. And then a note from DO-178 6442, code that introduces branches side effects are not immediately apparent at the source code level is part of the request. So this is what we're looking at specifically. In this example, we're looking at is rec knowable still, same function. We're starting with the same branch coverage of 332. And we're also looking at instruction coverage now, since we still have a deficiency there. At the bottom of the function, we have a stack check fail call, which is a system check for stack smashing. This is the end of our deficiencies that we need to look at, and in this case we're going to instrument the original executable with assembly coverage recording and exercise it so that it can jump through the fail or the false edge of this jump equal. So what you see here is the ASM layout of GDB running a copy of the instrumented FreeCiv server that has isrec knowable within the scope of instrumentation. This can either be done by instrumenting the singular translation unit that we're interested in or instrumenting the whole executable or some mix. At this point, I set a breakpoint for the position where I know I need to change a value in the running state of the executable in order to force the jump equal to fail. Do note that in this example, unlike, I'm going to flip back, unlike the source interleaving here, there are extra assembly instructions in the GDB layout due to the fact that you are seeing the instrumentation that does the recording of each statement, as well as the original code at this point. So once we get to our break position, see here, I've set a breakpoint. We've continued to hit the breakpoint. We can then muddy our RCX value, which is what we're going to directly use to test our jump equal. We can then continue on, exercise that path, fall through and fail on our jump equal. And then once we assume we've passed our point where we have our deficient coverage that we've recorded, we can excise the buffer, either printing it out from GDB or letting the application end naturally to write it out to the file system. So in reporting on that section of code, we have the same interleaving that I showed in the previous example. We're farther down in the code. Do note that this was a very long jump from the top of the function to the bottom of the function. That's why it just magically looks like there's coverage down here. Producing a report off the recording that we got from the executable in production mode, we see that yes, we have hit the fall through edge of this jump equal and executed index 1692. So we've proved now that we have gone down the path that we cared about from the previous view. I can then merge the coverage from the executable running in production mode with instrumentation around the function and translation unit we're interested in. I can merge that with the previous aggregate coverage of all of our unit testing instrumented for assembly, as well as the gap coverage for specific assembly instructions. Mix that all together and show that we now have our fall-through coverage here that was deficient before we started this testing. We've completed our instruction level coverage by making this call, the stack check fail, so we now have 100% coverage here. And we've moved our is reckonable branch coverage up. Do note, unlike the previous example, I did not go through and fix all the stack check fail calls or other calls of that class for this function, so we did not reach 100% coverage just because of the effort involved in chasing each one down individually and exercise them in production. So, in conclusion, don't panic. Tracing assembly code for structural coverage is tedious work. There's just no easy way to say it. Just never or not achieving the coverage for the other two branches had to be done here. Just the amount of time and effort to achieve these next two branches is significant. But because of that issue, it is important to make every effort to complete testing goals at high-level source, requirements, MCDC, and functional or production testing modes. It's super required because we've reduced our set to, I believe, within these examples, 18 gaps that needed to be covered across the whole translation unit, as opposed to starting from scratch on a completely uncovered translation unit that needs full assembly level coverage. And lastly, when we're focusing on this gap analysis or focus on getting paths that we consider gaps that are deficiencies from other types of testing, constraining the focus makes it easier to find the path that's necessary and documenting that path either through scripting or unit testing or parameterizations. And also, because we're able to amend that coverage or update that coverage with different small portions of unique coverage for specific testing purposes, it promotes a more collaborative coverage effort with individuals contributing partial coverage or gaps rather than overlapping their effort on shared code, specifically code like functions defined in headers and template instantiations. If the coverage can follow along with those constructions as a recording and then applied while someone is working on a unit test, we already start from a better position than starting from scratch each time we instantiate a function from a template or pull in a header defined function. So that's the end of the presentation, and now we can open up to questions if anyone has one.
That was great, Uwe. We got a couple questions that have come in. They seem to be related, so maybe you can, I guess, address them both at the same time. The questions are, how is the original assembly code instrumented, and how is the object code structural coverage merged from disparate executables?
Okay. So the assembly is instrumented through a tool set we've developed to inject assembly instructions at breakpoints where we can record straight line execution of assembly. If I bounce back here, a good example is just showing the assembly layout dump. What we've done is add intermediates so that we can record sections of straight line assembly. This is implemented in a tool set that means to kind of augment the original tool chain. So is a prefix to each compile, link, archive lines, like in makefile format, CMake, Eclipse, CDT, things like that. This instrumentation is unique to the function being instrumented, and instrumentation happens within the scope of a translation unit, like a C or CC file, after preprocessing. That instrumentation then produces coverage buffers for its execution, either through the halting of the application or through excising the buffer from memory during execution. And then this buffer can then be applied to the original source markup. So here I have a interleaved piece with both the high-level C source and assembly woven together, and I've applied a single coverage reporting buffer to this. But it doesn't mean that the buffer is tightly bound to this report. If we find that a buffer has meaningful data in separate places, specifically in this case, this is a shared piece of code. This meta-knowledge.c that we're testing and instrumenting is actually used in multiple pieces of, or multiple executables within this project. So it's used in both the server and client in this video game. And we can pull this buffing, this recorded buffer from an instrumented copy of either of those executables, as well as a unit test executable. And if a function is seen to be unique and present within those three items, coverage can be applied from any buffer with that unique identifier. And that's how we're able to go from, in this case, the server instrumented for isRecNoval and produce coverage that can be merged with the unit tests of the same function in question.
Are there files that are being merged? The data that's produced?
Yes. So I guess the best way to say it is, for the purposes of merging coverage from disparate executables, in the example we have here, we're merging a unit test executable's instrumented version of isRecNoval with the production instrumented copy of the server, where both the unit test and the server have the same instrumented translation unit that isRecNoval lives in. We can merge those two because we're producing a intermediate language for the assembly that allows us to see that regardless of position, the function as it appears in assembly has been laid out the same way. So when we instrument a translation unit, in this case meta-knowledge.c, we're producing a file that represents its assembly layout, its abstract syntax tree for the assembly of meta-knowledge.c. Once we've produced assembly coverage, or we've produced a coverage recording file, we can then apply that coverage recording file's data back into the abstract syntax tree for the assembly that we previously instrumented. So the abstract syntax tree can repeatedly consume coverage recordings. And the logic behind it is, if something in that recording happens to match a section of this AST, we will apply the coverage for it. So what you can do is preserve one of these, the assembly file, in the marked up assembly file, and apply coverage from different sources. One way we've been using this that's been very interesting is asserting that the assembly code produced in unit test is identical to the assembly produced for production. So that we found that if you produce a abstract syntax tree from the final product as it is seen in production, and then produce coverage recordings from the unit tests and try to apply them and none apply, that means that the unit tests have produced functions that do not look like what is resulting in the final product, or what will be eventually running in production. But the inverse, if you have multiple recordings of assembly coverage, each one with small gaps in them, you can produce multiple recordings, apply all those recordings to the same abstract syntax tree, producing a cumulative coverage report or an aggregate report from all those recorded products.
Thank you again, Uwe, and thank you all for attending. I highly recommend that you visit our website, parasoft.com, where you can find lots of informative content and collateral. If you want to learn more about C, C++ test, I've provided a couple of QR codes. The first one is if you want to try our products to contact us. The second QR code will take you to a self-guided simulated journey through C, C++ tests. You can also contact us by email, info@parasoft.com, and follow us on Twitter, YouTube, Facebook, and LinkedIn. Thank you again. Bye-bye.